All right. This is a little bit of a lesson on Le Chatelier's principle. And in this video, we're going to put some of the concepts that you have learned by doing some demonstrations or an activity or just watching some introductory videos into your notes. So basically, Le Chatelier's principle states that when a chemical system is at equilibrium, when a chemical system that is at equilibrium is disturbed by a stressor or a change, the system adjusts in a way to oppose that change. So this is really important. It goes back to that kind of idea that is stressor, shift, change in concentration. That is basically Le Chatelier's principle in a nutshell. Now, what happens to a system at equilibrium when it's disturbed is that the rate of the forward reaction and reverse reactions are temporarily unequal because it's adjusting to the disturbance. Eventually, the equilibrium gets restored again. So this is another one of those lessons where you are going to have to, at your discretion, pause and make sure you have the information written down into your notes. So if we go and we look at a make-believe system, and in this system, it's pretty straightforward. We have A plus B is in a equilibrium. That's what that sign means, with its product C plus D. So if we think about what we know about a system, is that if you were looking at reactants, A concentration, this is a graph of concentration over time. Now, if you start with your reactants, A and B, their concentrations are both going to come down, and eventually they hit the plateau, just like we've seen before in our introduction to equilibrium. B does the same thing. Concentration goes down and eventually it plateaus when equilibrium is met. C and D, their concentrations rise and then plateau. Now, this plateau that we see in this space right here, this is the initial equilibrium. If this system has a stressor, and in that stressor, we're going to remove A. So that means the concentration of A right here comes down. Because we've removed some of A, the system is going to adjust to counteract that disturbance. It's going to very quickly try to restore some of the A. Because the A concentration has decreased, right here in the red circle, we're going to see that the concentration of A then comes back up. So our equilibrium has shifted towards A plus B. Because it's making more A, so coming this way to the left, the concentration of B is also going to increase. C and D are going to decrease, like we see right here. But what's important to notice is that right here, we see that the equilibrium has shifted, but they all plateau again. So we see a new equilibrium happening. Eventually, the equilibrium gets restored. So when we think about what can we possibly do to disturb our system at equilibrium, what are the stressors? So you can stress the system at equilibrium by changing the concentrations of reactants or products. So that means that you can add reactants or products or remove reactants or products. You can change the pressure, you can change the volume, and you can change the temperature. And you change temperature by adding or removing heat. Right here. So this big black box I have here, this is Le Chatelier's general rule. If you add something, the system shifts away from it. If you add A, it's going to shift away from A and move towards C and D. If you take, it shifts towards. So if you remove something, the equilibrium is going to shift towards reestablishing that substance in the equilibrium. So if you add, it shifts away, and if you take, it shifts towards. So let's look at how some of our stressors can impact our equilibrium. So this is just writing out in detail some of the things that you've already seen so far. So the first one is change in concentration. When you add a reactant or product, the equilibrium is going to adjust to consume or use up the extra. So thus, it shifts away from what is added. When you remove a reactant or product, the equilibrium adjusts to replace what is gone. And so it shifts towards what's removed to replace it. I think I'm going to highlight here a little bit. Okay, so here we go. Sorry, this pen's not working. So, come on. Okay, there we go. Big ideas highlighted there. I'd probably underline or highlight this idea because it kind of summarizes it up really nicely. All right, the other thing is you just need to remember that this only works for gases or solutions. Adding or removing solids or inert gases, so gases that don't react, does not shift equilibrium. Please remember that adding solid does not shift your equilibrium. All right, let's look at temperature. So if you change the energy, so what I want you to do is recall back to our thermochemistry. When we have an endothermic reaction, we want to think about the energy as a reactant. It's on the reactant's side. When we have our exothermic reaction, we want to think about the energy as a product. It's being produced. So when we are thinking about a chemical system in equilibrium, we can consider energy as though it were a reactant or a product. If we add heat, so adding heat is that it shifts away, from the side with the energy. So if you add heat to an exothermic reaction, it's going to shift towards the products. Essentially, again, if you add, move away. And if you take away energy, it's going to shift towards the energy, towards making the energy. The same idea. Oh my goodness, that didn't work so well. Sorry, so the key with energy is consider it as a reactant or a product. And then the big idea of add, shift away, take, shift towards still works. Let's look at volume change. Now, some of you in 3U might have learned Boyle's Law. I don't really care if you know Boyle's Law, but what I want you to be aware of is that pressure and volume are oh, that's not what I'm going to do. There we go. So pressure and volume are inversely related, which means the more volume you have, there is less pressure. And if you have a smaller volume, there is more pressure. So think about a balloon. If you have a balloon that just is a little bit inflated, the balloon's not very tight. There's a lot of flexibility in the balloon. But if you have a balloon that's blown up a lot, it's a high volume of air in the balloon. And so, never mind. That doesn't work for this. Ignore I said that. Okay. So back to Boyle's Law. Pressure and volume inversely related. This is important. Okay. So if you are working with a system at equilibrium, if a volume decreases and pressure increases, equilibrium shifts to the side with fewer molecules. It does this to decrease the pressure. And if volume increases, then pressure will decrease and the equilibrium will shift to the side of the reaction with more molecules. So after you have this down, we will look and see what this looks like. All right, so to understand this, you need to know how many molecules exist for each side of the equilibrium. So if we look at our equation here, N2 plus 3H2 makes 2NH3. On our reactant side, right here, we have 4 molecules, 1 and 3. But on our product side, we have only 2 molecules right here. So it tells us, I'm going to scroll up here. Okay, so if we increase our pressure, we're going to shift right. So shifting this way, because it's the side that has the lower number of molecules. And if we were going to increase our pressure, we would shift left. I'm having a hard time with my stylus today. Okay. If the number of gas molecules are the same on each side, then the equilibrium is not going to shift. Okay. All right. Now that we've talked about concentration, energy, and volume and pressure, we need to look at changes that are not going to affect equilibrium. So these are things that even though if you apply them to a system in equilibrium, it's not going to shift the equilibrium. So one of them, the first one is a catalyst. I'm just going to scroll them all up here. Okay. So a catalyst increases the rate of the forward reaction and the reverse reaction equally. So a catalyst has no impact on the position of equilibrium. The only thing it does is affect the time it takes to reach the equilibrium. So adding a catalyst is not a stressor that will cause a shift and change in concentration. And then adding an inert gas. So these are gases that don't react. So our inert gas is a gas that cannot react with the system. What it does is increases the pressure, but the number of collisions for both sides, increases the pressure and the number of collisions for both sides because it's adding more molecules to both sides of the equilibrium. So because it impacts both sides of the equilibrium, we don't see a shift. All right, so those are the important pieces here that I think you should probably color code or highlight. Catalyst, rate of forward and reverse reactions equally, so it only affects time. And inert gas adds molecules to both sides, so we don't see a shift. So the last thing I would like you to do for this video lesson is go ahead and copy down this situation. And I'm just trying to make sure you can see it all. Okay. Copy down the situation here and predict the following shifts that will happen. So remember, we're adding a stressor, a shift, and then an adjustment in the concentration. So in this reaction, we have 2 molecules of SO3 is in equilibrium with 2 molecules of SO2 and 1 molecule of O2, and it's exothermic, so it's releasing energy like a product. So hit pause, copy this out, and try to predict the shift. Decide if it's going to go right or left. And when you've done that, go ahead and hit play back and check your answers. Okay, let's take this up. Oh, maybe my stylus is being awful, so I don't know how well this is going to go, but we're going to try. If we add SO2, by adding SO2, remember, if we add, we move away. So this means that we are going to move away from SO2, and SO2 is in the product, so we're going to shift left. Make a big L. Maybe not. Okay, there we go. If we look at increasing our volume, by increasing volume, we are going to decrease our pressure. And so because we're decreasing our pressure, we're going to shift to the side that would have more molecules. So because our reactants only have 2 molecules, but our products have 3 molecules, we're going to shift right if we increase our volume, because that means we're getting a decrease in pressure. Oh, that did not turn out. Decrease in pressure. I told you the stylus is being terrible. Okay, neon gas is added. So neon gas is an inert gas. So that means it's unreactive. So there is no shift. I'm sorry, just going to have to deal with mess, I think. In D, our temperature is decreased. So when you're decreasing the temperature, what you're really doing is taking away energy. When we take something away, we move towards. So that means that you're going to move right, because you're going to move towards creating the energy here. Oxygen gas is removed. Again, if you take, you move towards. And so our oxygen is in our products. So we're going to remove, the equilibrium is going to adjust to restore the amount of oxygen. So again, we're going to move right here. If we look at F, we are adding SO3. If you add, you move away. So the equilibrium wants to adjust to remove some of the extra SO3. So adding, you move away. We're going to move right. If we remove SO2, we're going to move in a direction to restore some of that SO2. If we take, we move towards. So again, we're moving right. If we add a catalyst, you should have said no shift. See if this one works out better. I can't. There's a lag, so I can't see actually what I'm writing. Yeah, I don't even know. That didn't even show up. Oh, nice. Okay, and our last one, we increase our pressure. So if we increase our pressure, the system wants to adjust to relieve that pressure. So increasing our pressure, it's going to move towards the side with less molecules to decrease the pressure. So this time it is going to shift left. Okay, so I have some practice for you to do on this, where you are looking at some systems and some stressors and just deciding which way it's going to shift, left or right. Eventually, we're going to start looking at what happens quantitatively to the equilibrium concentrations when we get a shift. But for right now, I just want you to practice being able to properly predict which way the system will shift based on what the stressor is to the system in equilibrium.